Okay, students, the next way that we want to be able to determine acidity and basic acidity in an environment quantitatively is by using a titration. So I've got this titration set up here. But let's talk first about the difference between quantitative and qualitative data. All right, so quantitative data is anything you can measure with exact numbers. All right, so we're doing math in order to get quantitative data, and we'll get definitive calculations. So when we solve for pH, that would be quantitative, for example, because you get exact pH values. Qualitative gives us non-specific numbers and this is non-numerical data. So in a science lab with acid-base pH stuff, we could use indicators to see a color change, for example. We know a pH has changed, but we might not know an exact value for pH. We just know that there's a range into which it changed. We also would use something qualitatively like smell or touch or anything like that. So qualitative data is a good place to start with experimentation, but we want to move that qualitative data to quantitative data to get more definitive numbers. So we solve for pH, but a way to actually find pH. So let's say we have a value of water that is acidified. We can use a titration to find the exact concentration of that if we have a water sample. So what is a titration? A titration is something that we can use in acid precipitation, but it's a very common experiment to determine the concentration of a sample that has an unknown value of hydronium or hydroxide. All right, so titration is a technique used to determine the concentration of a substance in a solution by adding measured quantities of another substance that is known to react to it. So basically you have an unknown acidic or basic compound, and you're going to react it against something that has a known concentration, and then you can compare the amount of time it takes to neutralize and the volume of the known concentration to neutralize. All right, and we indicate that by color change. So we're going to use an indicator, phenolphthalein, in order to do that. So this is your basic setup where you have a burette, and that's what this is right here. So if I go to my titration, this is something that you need to know. You need to know the materials for titration. So what do I have? I have a retort stand and clamp. I have a beaker that I'm going to use for waste. This is a burette. Okay, so this is a burette right here. And the base of the burette here has a handle that's called the stopcock funnel. I'm going to have a concentration. I have sodium hydroxide. Okay, and this is going to be my, I don't know the concentration of this yet, but we will find that out. Okay, this is my acid, so I know the concentration of this. This is 0.15 moles per liter. So that's going to be my titrant, because I know the concentration of it. And I'm going to put that in the burette, and we're going to find the concentration of sodium hydroxide, which will end up in my Erlenmeyer flask, which goes down here. And there's 4 Erlenmeyer flasks set up, because usually we do more than one sample. and then we get an average, and then if there's a sample that is above 0.1 to 0.2 milliliters away from the others, then we throw that one out. So you have to do more than one titration to get a good sample data. This is a pipette. Okay, so these are all my materials that I need. All right, I need my flasks, I need my waste beakers. I'm going to have smaller beakers to transfer the volumes of my titrant in my sample, and then I have my indicator, which is phenolphthalein, which will be a couple drops, and then we'll be able to get a pH value, and then we'll do a little math equation to solve for the concentration of the sodium hydroxide, because we don't know that. So here's what happens. All right, I'm going to take my sodium hydroxide. Okay, so this is my sodium hydroxide. I'm going to pour this into a sample beaker. Okay, I'm going to pipette out 10 mils. Okay, that's about 10 mils. So we measure to the bottom of the meniscus, and then I'm going to put this in my Erlenmeyer flask. Okay. And sodium hydroxide is a base. So this is my sample, because I don't know the concentration of the sodium hydroxide. So we're actually going to solve for the concentration of the sodium hydroxide once I've done my titration. We're going to use an equation to do that. And it's C1V1 equals C2V2. And C stands for concentration, and V stands for volume. Okay? So this is actually going to be the concentration of OH negative, which we're trying to find. I pipetted out a 10 ml sample. So I know, so this is going to be my KHP. That's my acid. And this is my OH negative. So I already know the concentration of my KHP. It's 0.15 moles per liter. Okay, so that's my C value. We'll get my V value from the actual titration when we've neutralized this. We're trying to find the concentration of the hydroxide, and I know that it's 0.01 liters. That's the volume of it, because that's how much I put in the pipette. So it's just a simple algebraic manipulation. So if I were to take a sample of acidified water, and then I were to titrate it, I would know the concentration of the water, and we could predict acid precipitation problems with that. All right. So here's my Erlenmeyer flask. I'm going to take my phenolphthalein. Okay, it's an indicator, and we're going to get a qualitative value during the titration, because what we're going to see is a color change. I'm going to put 2 to 3 drops of the phenolphthalein in the base. Phenolphthalein is pink in the presence of the base. And then what I'm going to do is take the KHP, and I'm going to pour the rest of the KHP Okay, so I'm going to take this KHP and I'm going to pour it into the beaker here, and then I'm going to pour that into my burette. I'm going to fill this all the way up to 0. And there's 25 milliliters of KHP in here. And I need to measure to the bottom of the meniscus. So I need to put a little bit more KHP in. Okay, now I have a little bit too much KHP, so I'm going to take some of that out. I'm actually going to move this and take some of the KHP out. Okay, so we're measured pretty much at 0 now. And then here's what happens with a titration. Now, this is going to be tough to do with one hand. Okay, so I'm going to take my hand off the stopcock here. And then I'm going to dump the KHP into the phenolphthalein, and we're going to swirl, swirl, swirl. And I'm going to look for a color change, and you can see that the color is changing. And I'm going to wait, I'm going to keep going until I see it get clear. Okay, boom, done. Okay, so you saw, it's a bit hard to do with one hand, but you can see that I've now observed a color change. Okay, so now I have the volume of the acid, and if I look at where it's at, okay, so we have about, so we read from the bottom, so the 0, it's about 12 point, it's about 12.7 milliliters. Okay. So we used about 12.7 mils. So my volume of KHP is 0.0127 liters. Okay, so I've got to convert to liters. So I've got my C1V1 equals C2V2, and then I can solve for, so I know how much KHP was required to neutralize the sodium hydroxide. I know the volume of sodium hydroxide, and I know the concentration of KHP. So now we can solve for C2 equals the concentration of hydroxide. Okay, so let's do the math. And then this is 1.15 times 0.0127 divided by 0.01. Okay. And I should get 0.19 moles per liter of OH negative. So that's the concentration. Now I'm pretty sure I overshot this, so it's probably not that concentrated, but I was doing it with one hand. So, but that's your general titration. I would do 3 more trials and see how closely related in concentration those trials were when I did the math, and whichever one was way different than the other 3 trials, I would disregard that one and then average out the 3 that were really similar. So I've got this, right? 0.9 moles per liter of OH negative. I can solve for the POH. Right? So remember, that is the negative log of hydroxide. So So I solve for this from my titration that I just did for you. I'm just going to make sure I secure my chemicals again. So once from that titration, I can solve for pOH, and that's the negative log of 0.19. Okay, so let's solve for that. So my pOH is 0.72, and I can solve for pH if I want. Solve for pH. Right, so I have my pOH. pH is 14 minus pOH. Right, so that's 13.28. 14 minus 0.72. So that is a very, very basic compound. Now, I'm pretty sure I overshot that by quite a bit. But regardless, you see you can see what we do with titration. Okay, so I'm going to go over this again. So the burette is where the titrant is. So the titrant is the molecule that has the known concentration. So it's the thing that we're using in order to find the concentration of an unknown. What we didn't know here was the sodium hydroxide. So that was my sample, and so the sodium hydroxide is the unknown concentration, and it's the sample, and it went in the flask. The KHP, or the potassium acid phthalate, was my titrant, and then we used the titrant and reacted it against the unknown sample, and we got the volume of the titrant required to neutralize the volume of the sample. And the sample was 10 mils. So from that, we were able to decipher, we knew the concentration of KHP already, then we got the volume of the KHP required to completely react with sodium hydroxide. So we had a volume of KHP, and then we had the concentration of KHP. We have the volume of the sodium hydroxide, and then as a result, we were able to solve for concentration of sodium hydroxide after that. And we used an acid-base indicator in phenolphthalein here. So we were able to get a qualitative value of neutralization when this changed color. So you saw that went from pink to colorless. And then we were able to quantify that by using C1V1 equals C2V2. And then once we had the concentration of hydroxide, solving for pOH and pH. Okay, so in your textbook, page 207, there's lots of data about titration here. There's a lab that you guys were going to do if we were in school. You can take a look at this. This is page 206. You're not necessarily going to need to solve for that anymore, but you should understand titration procedure. And we have C equals N over V, right? I use C1V1 equals C2V2, right? I know that the number of moles equals CV, so CV equals CV, and that's what I used here. You have, again, so here you have some sample problems for what I just did with titration, but you can see that there's multiple trials. So for this one, right, you'd throw out the dark pink one because it's not as similar. And then you would add up the 3 volumes that are within 0.1, 0.2 mils of each other, get an average volume for each titration. And then that gives you the volume of the titrant, and you'll know the concentration of the titrant. One thing you need to be able to read is burette readings. So in your textbook on page 211, this gives a good one here. All right, so if I look at these volumes, it's just asking you to read what are the volumes for each of the 4 burettes. So if I look at volume 1, right, remember we read the lower numbers are on the top, so we go from 0 to 25. So that guy is, volume 1 is like 4.3 mils. Okay, volume 2 is like 20.5 mils. Volume 3 is about 25.1 mils. And volume 4 is about 45.9 mils. Okay, so B says if burettes 1 and 2 represent the initial and final reading for a titration, calculate the volume of a solution used. So if I look at how to read this off a burette, right? I started at with my burette. I started at a volume of 0, and then I went down to 12.7, right? So to calculate that, my volume initial is 0, and my volume final was 12.7. So to find the volume used, it would be 12.7 minus 0. So I used 12.7 mils, so I know that that was the volume used in the titration. But you're not always going to start at 0, because you don't just top the burette up, because you can just reuse your values. Right, I don't need to, for this, right, there's 25 mils of KHP in here, but I only needed about 12.5 in order to neutralize the sodium hydroxide. So I don't need to refill that back to 0. I can just start at 12.7 and then go down to, wherever that would be down here by around 25. And then subtract the volumes from each other to get the total volume used in the titration. And that's what this is addressing here. So B and C. All right, so if I have a burette, so 1 is 4.3 mils, and that's my V initial. Okay, and again, this is page 211, number 42. My volume 2 is about 20. Let's say 20.55 mils. Okay, so 20.55 mils, and that's my VF. So my total volume that was used in that titration, if 1 and 2 are my initial and final volume, is 20.55 milliliters, which is my VF, minus 4.3. Okay, so 20.55 minus 4.3 will be the volume used in that titration. So I don't need to start at 0. I just need to know how to do the math on a burette. So 20.55 minus 4.3. So that titration used about 16.25 mils total. And that would be my volume I would use with C1V1 equals C2V2. Okay, let's answer question 43. Okay, so I'm going to remind you with this, the titrant is the chemical that is, or the aqueous solution that's we know the concentration of, and it's being used to neutralize the substance that we don't know the concentration of. So in the case of environmental chemistry, we'd be sampling water and then titrating it with a base because we suspect acidity in a water sample. All right, so the sample is what you will have in the flask, and the sample we don't know the concentration of, but we'll use standard volumes of it. And we see how much volume of the titrant we need in order to neutralize the sample, and then we can solve for the concentration of the sample as a result. And that is how titration works. Okay, and you need the pipette. Okay, right, and the pipette will be used to get an accurate volume of the sample that goes in the Erlenmeyer flask, which is what this is. We use beakers to put volumes of our chemicals that we're testing into the titration experiment. You need a retort stand, right? The bottom of the burette is called a stopcock. I need a funnel to put on top so I don't spill any of my titration. This is a good numerical response style question, like what do you need for a titration? What does your titration setup look like? Okay, so let's solve for question 43, and you can look at question 44, you should attempt as well. Okay, so if we look at question 43, the question says, use the following information to calculate the hydronium ion concentration in a sample of lake water titrated using a standardized solution of sodium hydroxide. So standardized means that we know the concentration and it has been titrated against something that has a very reliable concentration. Now, sodium hydroxide concentrations fluctuate quite a bit because it's a very reactive molecule. So if it's been standardized, we can reliably know what its concentration is. So you can see that the concentration of the hydroxide ions so what we're trying to find is unknown lake water H3O plus concentration, so acid concentration. We don't know what it is. Calculate the hydronium ion concentration. Okay, so the titrant, which is the NaOH, it has a concentration from the textbook of 0.000125 moles per liter. Okay? And the volume, right, so that's the concentration. My volume is from here. So my volume is 12.13 mils minus 2.25 mils. That was how much was required to neutralize the sample of acidified lake water. Okay, so 12.13 minus 2.25. And I'm going to get 9.88 mils. Okay, 9.88 mils of my titrant, and divide that by 1,000, and I have 0.009, right? 0.00988 liters. Okay, so I have to use liters because my concentration is in moles per liters. All right, now if I look at the sample, which is the water sample, the concentration, we don't know. That's what we're trying to find. Okay, but my volume, right, my volume is 10 mils, and it's always usually 10 mils in a sample. Okay, and then we do our math, and let's solve for the concentration of hydronium. So C1 V1 equals C2 V2, and the C1 are the titrant values. So I've got 0.000125 moles per liter, and I'm going to multiply that by 0.00988 liters. Okay. My C2 is what I'm trying to find, and the volume of the sample, which is the water, is 0.01 liters. So this is going to be divided by 0.001, and my C2 is going to be this multiplied by each other and then divided by 0.01. So 0.000125 multiplied by 0.00988, and that is divided by 0.01. So my concentration of hydronium is 1.235 times 10 to to the negative 4 moles per liter. Okay? So I can solve for the pH as well if I want, right? pH equals negative log of that. Okay, and then the negative log of 0.000125. Right, 1.235 times 10 to the negative 4. My pH is 3.9, so that's a very acidic sample of water. Okay, and that's titration. In your right, so there's right, CV equals CV. This is all in here. You can find concentrations of an unknown substance. Acid-base titration, right? We're looking at neutralization. That's what we're doing with the titration. We're neutralizing in order to find concentration of an unknown sample. All right, so that concludes titration. I'm going to post one more video today looking at acid-base indicator ranges and then just finish up this unit. Okay.